this length right here is 1, and then each of these pieces here is half, right? So go through and see if you agree with all of the different measurements that I've added in. See if you can understand why those are the measurements. Not on the bench. No, it's only forces acting on the bench. Okay. All right, so somebody tell me how I came up with the 3 meters. All right, Garrett. Very good. I subtracted the 0.5s off the end, and that got me 3, okay? Who can tell me how I came up with 2 meters? Okay, Graham? Very good. I subtracted 1 meter from 3, and that gave me 2. Who can tell me how I came up with 1.5 meters? Siobhan?
The total bench is 4 meters, and you're trying to find the center, so you have the 0.5, 0.5 on the other side. That's like added together, and then you subtract that from 4, and you divide that in half, and you add it to 1 on the side. Yeah, I don't think that way.
Okay. So there are a couple of different ways, right? We could divide the 3 meters by 2, and that gives us 1.5. That's probably the easiest. Okay. Or you could go Siobhan's route, and we could subtract 0.5s off the end, divide the 4 by 2, add a 0.5 back. So whatever, you know. All right. You're so good. But the point is there's multiple ways to get there, okay? But you have to get there. So if I do some kind of a similar question on a test or a quiz or something like that, you obviously need to be able to figure out those distances, okay? All right, now let's see. What was the question here? Where they want to know all the forces in the picture, right? Okay, and we know the girl's 55 kilograms, and we know that the mass of the bench is 10.6 kilograms, okay? So what do you think that we're going to do here? What do we always start with when we're doing these static equilibrium things? We did that already. Okay, you're going to split it into translational motion and rotational motion, right? Okay, so let's do that. We've got our translational motion over here. Okay, so let's start splitting these into translational motion, all right? That's going to be with what? F-net statements, okay? So talk to me. What should I write down as my first F-net statement? What kind of acceleration? Okay. And since we're in equilibrium, what's that going to be? Hey, what's up? I don't know, Ken. Are you asking to charge your phone? Well, he can handle his own business. All right. What else? You can't cheat code your way through me. All right. What's our next F-net statement going to be? Okay. So let's do that then. We've got the sum of all the forces in the y-axis. Who can help me out with that? Kathy? Okay, we'll put this in the right order. Okay. All right. Okay. On. No. There's 2 forces of gravity acting in this problem.
Oh, on the person.
Okay, so force of gravity on the girl. What else? Good. Minus the force of gravity on the bench. Okay. Now what do I do? Set them all equal to each other, okay? So I'm going to say here, force A plus force B minus force of gravity on the girl minus the force of gravity on the bench equals 0 newtons. Now, do I know the mass of the girl? Yes, I do. Do I know the mass of the bench? So could I figure out both those forces? Yeah. Do I know the applied force of of leg A? Do I know the applied force of leg B? So I have two unknowns in this statement. So will translational equilibrium statements help me this time? No, they won't. So I need to move over and do my rotational equilibrium statements. What do I use over there? Torque. All right, so we're going to do our torque net statements. So what's the first one going to say? No. What do you have to do before we can make any torque statements? We need to pick an axis of rotation, okay? Okay, so where do you want your axis of rotation to be on this? Okay, so I'm hearing FA or FB, and Adams correctly said on the unknown. So it would be wise to choose an unknown, and then I heard both of the unknowns, right? So we just have to choose one, okay? What would you like? All right, I'm hearing a bunch of FBs. So we're going to choose this as our axis of rotation, and that's where the torque net is at. So when we do our F net statements and we say, X or Y axis, that's fine. And when we do our torque net statements, we're going to say that this is the torque net. We're going to say where the axis of rotation is at FB. And since this is rotational equilibrium, what will that equal? 0. What? 0 what? Newton meters. Very good. Now we're going to do the second torque net statement. So we've got torque net where the axis of rotation is at FB equals, what are we going to write down? Yeah, the sum of all of the what? Torques, okay? Sum of all the torques. So tell me one of the torques we've got in the problem. No, it's not a torque. You stop saying forces to me. That's translational. I'm asking you about rotational. So, torque caused by force A. All right. So we've got the torque caused by force A. What else do I have? Okay, the torque caused by force B. What else? Okay, the torque caused by the force of gravity on the girl and the torque caused by the force of gravity on the bench. Now, you'll notice I put no signs in between those things. I don't know if I'm adding or subtracting yet. What do I need to do, Isaac? Do the right hand rule. So, let's go back to our picture. Put your right hand on the axis of rotation. And let's find the sign for the torque caused by the force of gravity on the girl. What's that one going to be? Positive, because it's going counterclockwise, or your thumb is coming out of the board, okay? All right, so now what about the force of gravity caused by the bench? That's positive. What about the force A? That one's going to be negative, right? What about the one caused by force B? There's no torque there, right? All right. Okay, so we said that torque A, or the torque caused by force A, that's negative. This one goes away. And then we said this one's positive and that one's positive. So now what am I going to do? Set them equal together, right? Set them equal to each other. Okay, so we're going to say that the torque caused by the force of gravity on the girl plus the torque caused by the force of gravity on the bench is equal to the torque caused by leg support A. All right, so at this stage, what are we going to do? After I've got my torque statement, what do I want to do now? Expand it using the torque equation, right? Okay, so what is the equation that I would get from the first one here? What would I say? First off, I guess let's write down what is the torque formula. Torque equals times sine of theta. Very good. Okay. All right. Now let's expand torque caused by the force of gravity on the girl. What am I going to write? Okay. So Graham's actually gone another step further, and he knows that the force of gravity is its own formula, and he expanded again. So he's going to say the mass of the girl times little g, and all of this is the force of gravity on the girl, times, what's the next piece? The lever arm out to the girl, times, yeah, the sine of the angle theta. Theta in this case would be what? 9 degrees, so the sine of 90 is 1, so we don't have to mess with that. What's up?
You're going to expand the other two, and then there's gravity on the right side. So the gravities would cancel, correct?
Good job, Siobhan.
I'm trying to go ahead.
All right, so what about the force of gravity on the bench? What am I going to say? Equals, now the sine of force A. What am I going to say? Not the sine of, the torque of force A. What am I going to write? That's an applied force. Right. Yeah. All right, so force A times lever arm out to A. And then, of course, that one sine of theta would be 1 as well. So, good. Now, actually, Shabam, unfortunately, we don't have G on both sides of the equation, so no, we can't cancel them this time. Okay, so let's go ahead and do our last little piece here. What am I going to do to get this force A by itself? Yeah, we need to divide by lever arm out to leg support A on both sides. Yes, please do. All right, so get your calculators out if you don't already have them out. Go through, and let's get a force A. And I'm going to want every single digit, and then I'll want the sig fig answer. No, but you can come borrow a calculator. Yeah, it's in the drawer underneath the remote control over there. Yes, the lever arm, by definition, is the distance from the axis of rotation out to the force causing the torque. Yeah, she would be 1 meter away from. Hold on. She's not 1 meter away from leg support A. She's 1 meter away from leg support B, right? Okay, yeah. So from the axis. Oh yeah. Never mind. Yeah, that's right. Yeah, 1. Yeah. Well, it's out to the center, so it's from the axis of rotation out to the center of the bench, because that's where the force of gravity is acting on, the middle, right?
What?
You bet.
No, we don't need it. So it'd be 0.5. The distance is the same. I'll drew my picture.
Okay, so let's help me fill in all this stuff so that we have a complete, we have it all complete on the video. So what's the mass of the girl? 55 kilograms times 9.81 meters per second squared times 1 meter for our lever arm, plus, what's the mass of the bench? Okay, so go through And who's got my answer for me? Somebody should have it by now. Garrett? No, I want every digit first and then sig figs. Okay. Now, how many sig figs should our answer have? 2. So what would we say here? All right, cool. So that's one of them. The force generated by leg support A upward would be 230 newtons. Now you have two choices. You can go back through all of this rotational equilibrium statements again by selecting your axis of rotation to be at the other side of the bench and solve for force B, or we can go back to our translational motion equation right here and solve for force B now that we know what force A is. All right. So let's rearrange then to solve for force A. No, excuse me, force B. So, yeah, so we're going to say force B is equal to the force generated by the girl plus the force generated by the bench minus force A. Y'all agree with that? Okay, so then let's go ahead and plug that in. What is just the force generated by the girl? Yes, what is that? 539 point what? Newtons. Plus, what's the force generated by the bench? 155. Yeah, I don't want the lever arm. Minus, then we're going to put our 231 point, what is it, 845? 843? 843. And I want every digit, and then we can sig fig that. Okay, so Josh, what you get? That was a naked number. Newtons, okay? And so with the correct number of sig figs, all right. So which leg is giving the greater amount of support right now? Force B, all right? So leg B is having to generate a larger upward force than leg A. Any ideas as to why? Yeah, the girl is closer to leg support B, so it's having to put more upward force. Yeah, okay. Yeah, well, downward force, and pressure is force over area. So, yeah, the closer she is to leg support B, the more force is on that side of the bench than the other side. Okay. All right. Any questions about that? So let's kind of review here all these static equilibrium problems at large, so that you have a game plan, an attack method every time you're going to get any one of these kind of problems. Okay. First off, you need to draw a picture if there's not one provided. Okay. Then what do? We draw our forces on top of our picture. Okay. Then what do? Yeah, then we split it into translational equilibrium and rotational equilibrium. And then what do? Then we can do our F-net statements on which side? The translational side. And then what? Then we're going to do our torque net statements on which side? Rotational. You'll, of course, need to make a decision on which one is going to be most useful. If you can do all of the forces with just the translational statements, do you need to bother doing rotational? No. Okay? If you can't do them with translational, then you should go do the rotational ones. if, like in this problem, you get to the end and you now have two choices, go back through all the rotational stuff again or go to translational, make the decision about which one's going to be easiest for you and take that route. That makes sense to everybody? Remember, after you do your torque net statements, you expand it using the equation, okay? That's a lot of times. Josh, you're driving me insane. Please stop that. Make the connection that when you've written your torque net statements, you've got to expand it. Because a lot of times you'll get to that point, you'll remember, okay, I can do all this stuff. You'll even remember to do the right-hand rule, and you'll put the signs in there, and then you'll be like, I'm stuck. I don't know what to do, okay? Remember to expand everything, okay? When in doubt, try and expand it, okay? All right. Oh, yeah, I do have some homework for y'all. Thank you. Yes?
Can it not be due tomorrow? We do have one.
Well, that's why I'm making a video. That's why I'm making a video. Yeah. So.
Yeah, we will. No, we will not. Wednesday we will be in here. Because it goes first, second, third, fourth, skip fifth, and go 6, 7, 8. Then fifth. That's such a weird schedule. Yeah, we do. Such a weird schedule. What? No, we're playing Kent. It's only 20 minutes. Yeah, we play poker too. Okay, thank you. I like this. This is a good amount. I like that. I can appreciate it.
Well, I'm so glad that you approved. That was my key, determining factor on how much I should print out. It's like, will Graham accept this? Okay. Take a second, write this question down, draw that picture, and then we'll move on.
Wait, when's it due?
Let's say tomorrow.
No, not tomorrow. We have a lab.
Oh, that's true. You got a lab due. Okay, fine. I will have mercy on your soul. We can do it on Wednesday. Yeah. Wednesday. No, this homework is due on Wednesday. Labs are due tomorrow.
Yeah, this lab is super hard.
No, it isn't.
Already finished it?
Y'all are so.
I haven't even started it.
Really? Dang, I thought that I fixed it. I really did. Late. Well, that's why I teach science, so there you go. Oh, well, you know what? I Infinity fixed it. Okay, there. It's all fixed.
Stop using ladders for problems, apparently.
Yes, great.
I didn't know this thing at all. Wording wasn't a very awesome. I got a fortune that said you should focus on the color purple because it'll give you good luck.
That's not very
Isn't that one of the ones you have a hard time seeing? Yeah.
That's why you gotta focus.
Oh my gosh.
Wow. Oh, hey, UIL people that didn't show up, you owe $8.
I know.
So.
It's only Brady.
Yeah, okay. Yeah, I need to tell those freshmen also.
Brady, you owe $8. I know. Well, no. Brady, do you need to borrow $8? Yes. I guess it's the same. What? No.
Nice businessman over there. It was good.
So he owes you $18, but it's okay because all he has to pay is 10. Yeah. I called those cookies at home? What was that? I remember that was loud. What cookies? You give them cookies? So what are the That's like child labor. You tell them to do some problems. It wasn't even him who got them. What are the forces being exerted? What are the forces exerted on right now?
Well, what's in static equilibrium?
I don't know. It doesn't say the problem.
True. You have to determine that.
Everything. He was trying to make a do you not remember who did the little meter stick thing?
Good job.
Yeah, Josh.
Okay, did we get that all written down?
No, there you go. Why are you like making all your people wait 55 minutes?
Why not?
You can. This is Jesus.
I don't know, but that was hilarious.
That's 121 pounds.
It's like, that's not horrible.
That's less than average.
That's like what Shabam weighs. Or Brady. Are you 100 and something, 20? 35? Nice. Yeah.
Next week it'll be gone again. No, we will not.
Is it gaining pure muscle, Gary? Yeah.
You go here. You go.
He wants to tell me. Yeah,
So it's all that altar wine. So yeah, for communion. All right. So we're good. What? I don't know. Mark and Desire, not here. Poor Wana, yeah. Okay. So let's go ahead and take a second to put all of your forces on the ladder there. You know, what you think the forces are acting on the ladder and which direction and all that kind of stuff. And then we will confirm. Also, go ahead and put in any lever arms that you can calculate, any distances that you think you can come up with. Well, they call it it would be like a 3, 4, 5. Yeah, so maybe.
Oh, got you. So it's actually a 3, 4, 5, which is not a 30, 60, 90.
You use your trigonometry stuff.
Oh yeah, I totally forgot we had that. Wait, Leslie, I have a question.
Yes.
Where would the force of gravity on the ladder be going?
Well, which way does the force of gravity point,
It goes
Siobhan?
down, but where would it be? Would it just be at 2.5? Wherever 2.5 is.
My turf. Okay, so let's go through and look and see if you came up with all the stuff I came up with. All right. So where the ladder touches the wall, there's going to be a normal force. Okay. Where the ladder touches what? Ah, jeez. Ah, jeez. There we go. All right. So where the ladder touches the ground down here, obviously there's a normal force from the ground, but then also the ladder would have a tendency to slide along the ground towards the left. That means that friction would oppose that motion and point towards the right. Okay. Then, of course, we've got our dimensions on our triangle. We've got 5 meters. We've got 4 meters. So we could use Pythagorean theorem and figure out what this distance down here is, although I don't know why that would be helpful to us. We could also figure out what this angle is here. Knowing this angle allows us to use some geometry and what is that? Opposite interior angles or something like that. So we know what this angle up here is where it touches the wall. We also know the midpoint of the ladder is going to be 2.5 meters, so that's where the force of gravity would act, the center of gravity. The painter was 3 meters, so it's a little bit further than the center of gravity, so we've got that one there. Questions about any of that stuff? Well, let's see. If I was going to solve for this angle, that's opposite to this one, right? So I'd probably say the inverse sine of 4 over 5. Okay? Worried? Okay, so after you put your vectors, your force vectors on your picture, what's always your next step? Translational and rotational motion, right? So let's do our translational motion statements. What are we going to use with that? FNet statements. Okay. So what axis are we playing in here? Yes.
Oh, I totally got that.
All right. So let's do the y one first. FNet and the y-axis equals. Now, what's that going to equal? Newton's second law. Thank you. And what's that going to equal? 0. Because why? Because we're in equilibrium, and that means no motion, right? It's not moving. Okay? All right, now let's do all of our some of our forces, right? In the y-axis. Yes. So what forces do we have here? That's not in the y-axis. Okay. Normal force from what? Okay, cool. So we've got the normal force from the ground. Okay. Do I subtract it, add it? What do I do? Subtract. All right. So we can say the force of gravity from the person. Okay. The painter. All right. What else? Okay. The force of gravity on the ladder. All right. Now, now what should I do here? All right, set them equal. So we can say the normal force from the ground is equal to the force of gravity from the painter plus the force of gravity from the ladder. Y'all, nice. Okay, so we know the mass of the ladder, I believe. We know the mass of the painter, so we can solve for the normal force on the ground, right? Or from the ground. So let's do that. So what is the mass of the painter? Times 9.81 meters per second squared plus, what's the mass of the ladder? 12 kilograms. Is that 3 sig figs or just 2? 3? Okay, kilograms times 9.81 meters per second squared. All right, so what is the normal force generated by the ground on the ladder with every digit? Coco? Now, the whole point of this question is we want every single force, right? Okay? Now that frictional force, let's talk about that for a second. What's the formula for friction? Mu times the normal force, okay? And we just got a normal force, so that may come into play in a minute. May not, but it may. All right, so we did our F-nets in the y-axis just then. Let's go ahead and do our F-nets in the x-axis now. What's the F-net in the x-axis going to be?
Is that last question we just got with 2 sig figs is this?
Yeah. Okay. I believe so. Isn't that what one of the questions was? Like, find all the forces? Isn't that the question? Okay. And the wall. Okay, so yeah, so that's one of them then right there. Let's, how many sig figs should we have there? 2. All right, so 660 newtons, right? So that's one of your answers. Okay, so then what's the next thing we're going to say? Mass times acceleration in the x-axis. What's this going to equal? Y. Equilibrium, okay? F net in the x-axis equals what? Okay, so we're going to say our, what kind of friction is this going to be? Okay, static friction minus what normal force? Normal force from the wall. Okay, now what do I do? Set that equal. All right, so we're going to say the static frictional force is equal to the normal force from the wall. Now, what to do? Okay, so what's the equation for friction going to be? All right, did I give you a mu? No. So, that may not help this time. We've got 2 unknowns. Graham was the only one. All right. So the last time we did our F-net statements in the x-axis, and we said that the frictional force is going to be equal to whatever the normal force on the wall is, right? Which we didn't know. So what do we decide to do?
We were talking about mu and how we didn't have.
Yeah, we don't have mu either. So what's the next thing we need to do here? Well, did we do F-nets in the y-axis yet? Yeah, we need to do our F-nets in the y-axis. Yeah, it says x-axis right here. We did the y-axis? Did we do that first? Okay, I see it. All right, cool. So then, yeah, we need to do the rotational. Okay, rotational. What belongs in the rotational section? Torque net statements, okay? So we're going to say torque net is going to be equal to what? 0 Newton meters. Now, in order to do a torque net statement, we have to do something. Yeah, we need to figure out what our axis of rotation is going to be. So let's go back and look at our picture here. And remember, we should be smart about picking our axis of rotation, right? Where should we pick? Something about the unknown needs to be the axis of rotation. So we discovered that we had 2 unknowns. We don't know what the frictional force is right here. We don't know what the normal force on the wall is up there, right? So which one would we like to pick? Okay. So, well, either way, let's, we were told by Shivam just now to select this as our axis of rotation. So let's go ahead and label that. And then on our torque net statements, we'll make sure that we claim that. We're going to say that torque net, when the axis of rotation is at the frictional force, is going to be equal to 0. And then we'll do our next torque net statement. Torque net, when the axis of rotation is at the frictional force, is equal to what? Is sum of all the torques, right? Okay, so we need to go through and see which forces are going to cause a torque on this system, right? So, what do you think? Where? Yeah, okay. So Adam says that this force of gravity on the ladder, that's going to provide one of our torques. Okay, the force of gravity due to the painter, that's going to cause another torque. What else? Right, the normal force from the wall. Yeah, these two down here, the frictional force and the normal force from the ground, since those are at the axis of rotation, their torque's going to be 0, right? Okay, so we're going to have 3 different forces causing a torque, so let's go put that in our rotational system. So what do you want to say first then? Okay, so the torque caused by the normal force from the wall. Well, we're not going to do any signs yet. We'll go back and do that in a minute. What's the next one? Okay, so the torque caused by the force of gravity from the ladder. And then the last one? The torque caused by the force of gravity from the man. Fight the man. Okay, now we want to go back and get our signs. How do you get the signs? Right hand roll. Very good. So, yeah, take your right hand, put it on the axis of rotation, point your fingers along the lever arm, bend them in the direction of the ladder force. Which way is this going? Your thumb's pointing inward, and we're getting what kind of a rotation? A clockwise. So is it going to be negative or positive? Negative. All right. So, all right. So Brady told us that the one from the ladder and from the man are both going to be negative. Okay. Now, what about the one from the wall? What are you going to say there? That one's going to be positive. That would give us a counterclockwise. So we can just go ahead and slip our signs into that statement. And now what do we do with those statements? Set them equal. So we're going to say that the torque caused by the normal force of the wall is equal to the torque caused by the force of gravity on the ladder minus or plus the torque caused by the force of gravity from the painter. Yes, sir.
So, the normal force, that's the one up here, right?
Mm-hmm.
So how do we do like the right hand?
You put your hand at the axis of rotation, point your fingers along the lever arm, bend your fingers in the direction of the force, and my thumb points out, and my hand would rotate in a counterclockwise direction. Okay? Now, what do I do with this new equation here? Yeah, I need to expand it with what? The torque formula, which is?
The force times the lever arm times theta.
Very good. Okay? So, looking at my force normal there, I'm gonna put that down. Normal force from the wall times, now what's the lever arm from the axis of rotation out to the normal force there? 5 meters. Now, we need our angle theta, and by definition, the angle theta is the angle between the lever arm and the force vector, right? So, if this is my lever arm right here, and this is my force vector here, then I need this angle, okay? So we're going to say our 53.13 degrees. So that's what we're going to take the sine of. Equals. Now let's do our next one there. What are we going to say? Well, we can expand that too, right? Mass of what? Okay, so we can say the mass of the ladder times what? Little g times what? The lever arm out to the center. And I guess, you know what, let me just go ahead and put values in here. What's the mass of the ladder? 12 kilograms times 9.81 meters per second squared times, what's my lever arm? 2.5 meters. Now, what's the angle going to be there? Angle alpha. So what is that? All right, so times the sine of 36.87. All right, plus, now we need to do our torque caused by the force of gravity on the painter. So what are we going to say for that one? 55 what? Times 9.81 meters per second squared times 3 meters. Very good. Times the sine of that same angle, 36.87 degrees. Now, we've got some simplifying that we can do over here on the right-hand side of this equation. And then once we've done that, we can divide by 5 times the sine of 53.13 so we can get our normal force. Okay, so let's go ahead, get our calculators out, and do that. I suggest you simplify first and then do your division. But if you want to try and do it all at once, then that's your prerogative. Yeah, very good. Since we're going to be hitting a sine, cosine, or tangent button somewhere along the way, you need to make sure you're in degree mode in your calculator, or you're going to get the wrong answer. All right, so who's got the normal force exerted by the wall for me? All right, Brady? Yes. Yeah, give me 6. Well, no, well, yeah, 6 figs. Yeah.
Okay, we got 290 newtons.
290 newtons. Raise your hand if you agree with that. Okay, excellent. Now, remember, what was the question here? What was the goal of all of this?
To get all the forces exerted on the ladder.
Yeah, we want all the forces on the ladder, right? So we've got the force of gravity of the ladder itself. We've got the force of gravity from the painter. Now we've got the normal force from the wall on the ladder. And the last thing we needed was what? We need that frictional force and do we need the normal force from the ground still?
No,
we got that already? All right. Yeah, so.
Do we need to do the
Very good.
the force of the painter on the ladder too?
Yeah, we did that already.
We did?
FG of the man.
Yeah, but
Did we do it? I don't know if we did it. Yeah. Okay, so we know that our frictional force is also going to be 290 newtons. Okay. There is one little hiccup here that Brady neglected to tell us from this normal force on the wall. What do we need to say here? Yeah, the direction. It's pointing to the left, right? So what should we say? It's negative, okay? All right, so that's going to be negative 290 newtons, and the frictional force is going to be a positive 290 newtons.
Wait, how is this? What is that? Because that can cancel out. So the force of gravity.
All right. And then you're going to go through, obviously, and give me the force of gravity acting on the ladder. And you'll need the force of gravity acting on the painter, if you haven't calculated those already. Anybody got one of those for me? Graham? You got one? Yeah. All right, Josh? Okay, the painter is negative 540 newtons.
Negative 1.
What kind? Negative. Okay. Newtons, very good. Are we okay with all of that?
Wait, how did we get the because it cancels.
No, it's equal to the normal force from the wall. Yeah.
Right, but that cancels because one's negative.
Exactly, yeah. Now, anybody have any other questions? And this right here is where we see that it's in our FNet statement, the x-axis. That's why we can set those equal. No, not in this case. But now, Sean brings up a good point. If I want to know what mu is, if I wanted to know the coefficient of friction between the ladder and the ground, can I solve for that now? Yeah, with a formula. So what is the formula for friction? Yeah, mu times the normal force. And so I could solve for that. What do you think that's going to be? Should be, yeah, it should be 1, right? Okay. Questions All right, we are done with court. Thank you for learning.